All right. Time for the last talk. We see the best for the last. My friend, Naihuan Jing from NC State, he will tell us about the Q and Q characters and the vertex of it.
Thank you very much. Also, so I'm going to talk about actually starting from very basic things in the representation theory. The first thing you start with Green's formula, then you have the then later on you have Schur's work and generalizing Green's formula, Schur's character formula, double symmetric group. And later in the 30s you have the Schur formula. And then so our starting point is actually joint work with the Wei Chang and Igor Frankel and the I mean, I'm sorry, 2000. So if you start with the, so if you, so if you have a finite group, and then consider the grid product, and then you consider all the space of all the irreducible characters or the class function. And then you can see all the summation of these, and this can be realized as a natural Fock space. And in particular, of course, that if you essentially when you tensor this the group algebra, and then this can be essentially realized in the special case that when this is the subgroup of SL2, in the so-called Mackay correspondence of these, this can be realized. These affine is actually the number 0 for the double affine reality. So the very same construction, if you throw away about this, say if you consider more general, just G, then all these vertex operators still make sense. And this vertex operator exactly can this part exactly can tell us that what's going on to the realize the Schur's character theory of GRMS. And then you can ask a question, of course, that in the 50s, the Green actually has a important work. It produced all the irreducible characters for GRN over finite field. Of course, that the generalization is more. This is more involved because over here that the things are simpler because all the classes actually corresponding to power sum, and over here this is more quite complicated. And what I'm going to do is actually try to generalize this. Yes.
What is CQ gamma?
This is some group algebra. So I don't. I mean, I'm just saying that there is some other factor. The algebra, the group, the lattice, the group lattice, and you take the group algebra. So for these, and so in other words, I'm going to concentrate on the following thing. So Gn, I will define as GLN. And for these, I'm going to need the Frobenius. This is Frobenius. And then I consider these this Qn. So I have this token, and it is exactly this Fn. The fixed point is the Fn. So going to need also need the F orbits. The F orbits of the multiplicative group. So this for convenience, I'm going to denote it as F. The reason I'm going to do this is that, like, if you take a finite group, if you say that you ask yourself the basic question, how do you describe all the irreducible characters? You start with conjugacy class. You parameterize the irreducible characters. So now the first thing is that what are the conjugacy class? GIF, GM. Well, for this, and if you take any element in GM, and then these, you get Fm vector space. This is the F, and by letting G acting on V, T, and you get this is a T acting on V equal to T acting on V. So now this is the FQE module. So for this FQ module, then it turns out that the G conjugate to H, if and only if these two spaces are isomorphic. So therefore, then the conjugacy class will be completely determined by, if you look at this primary decomposition, and therefore the primary decomposition of this, all these primary decomposition depends on the irreducible polynomials. Well, the irreducible polynomials of over the Fn are exactly given by this by the F orbit minus, you don't want the 0 element. So you consider all these, actually all the irreducible polynomials are given by this F orbit. So for that reason, I mean for these, so therefore you have this effect. Actually, this is green. The conjugacy class what you want corresponds to so-called color partition. And you have to put the weight. Weight is the color partition. And these are colored by the following thing. So you have a mu equals F. So this is colored by phi. So phi is the set of all the irreducible all these F orbits. So these are all the F orbits of course a certain degree. The degree condition is this. So you have your the F running through the F orbit, but then each irreducible there is a degree, and then you want all this degree to be exactly equal to F. So that's the restraint. So in order to have all this color partition and corresponding to the irreducible the conjugacy class. As a result, that all these certainly this corresponding to all, I can also label all the irreducible characters by lambda. But then I cannot use F, so I must use the dual of these of the character group of the orbit. So then I can get all these. Then I immediately know what is this space. So in other words, I have this FT So now we know that what is this space? This space is really just the summation with this lambda equals m. Then irreducible characters. Abstractly, and this is. So the question is, how do we realize these irreducible characters?
Well, sum over all n, first thing, the left hand side is no g in the index.
In the G, yeah, I mean, not over there. Sorry. This is yeah, you're right.
So the left hand side rg, there is no g. Now g has no meaning.
Well, I guess you can forget what.
G and infinity.
Yeah.
So that's not the risk for that.
It's not. So, so now you have these, that of course, so the very forbidden formula is that, well, you realize those things in the forbidden case, you realize those irreducible characters by the Schur functions. And then you realize the conjugacy class by the power sum, symmetric function. And then you take the inner product, so you get a character. So, but how can we do the same thing for this GIM? For this GM. Well, I mean, of course, you can still do the irreducibles over here, so that's what I'm going to start. But I have to make sense that I have to first of all, you have to make sense of what the irreducible mean. So at least I can formally, first of all, I mean, here this space, there is certainly a Hermitian product. So if I take the two class. So we can define in the homogeneous class, I mean, homogeneous class function is defined in the usual way. And then you extend this by, I mean, the extension to this. So then you have this. So now I want to be, besides these irreducible characters, I can also consider some very special characters. So I can consider these, I can also, we can talk about some multiplication. So how do we do the multiplication? First of all, you take the, if there is a composition, then you can define this parabolic. What is GLJ? And J, and then you require this. This actually coming from invertible, the regular element here. So this is parabolic, and then you take the two class, and you take the product by taking the doing the induced. Take the MM. Say this is the class in the GM, and this is the class in the class function over here. So then you have this. Then this becomes a commutative under this multiplication. R becomes commutative associative value. So now I mean, besides the irreducible characters, we also got another one. So you can take the characteristic class functions on all the irreducible on the conjugacy class. So, so here you can also take so you define this I mu to be the characteristic class. Characteristic function on the class, on the conjugacy class CV. And although it's not easy to compute the structure constant of these, but it turns out that the structure constant for this one is something well known. That's why that was what the Green's work was actually identified for these characteristic conjugacy, the functions. The structure constant is actually exactly the O algebra, the simplest O algebra. So so this is we have this Green. So it turns out that the time mu times this is G and these constant, the structure constant, uniquely determined by, you see that although under the multiplication structure, there is some generators. The simplest generators are those coming from elementary symmetric function. So for the elementary symmetric function, these are constant are exactly computed by Green. So here, so I'll write the simple. Say if we multiply this by m, q, and then this is given by lambda and u, and then there's product of this lambda I prime minus lambda I plus prime, lambda I prime minus mu I prime, and then base at q. All the q number in over here in this talk will be combinatorial q number. So over here, this is the dual partition. Young diagram, you take it to flip, and over this n lambda is the this is a partition. Then you can flip, you get a dual partition. And then for each partition, you can define this n lambda. So then you have this uniquely determined by products of this thing. I won't write down the general, but essentially that you just need this structure constant to identify everything. So that was the Green's work over there. So what we're going to do is that instead of using this symmetric function, also we have the motivation is that also we need to construct some object where we are able to compute, and we are able to compute the characters to really compute all the characters. Formula, I'm going to write down the exact formula for that. That's the purpose. So that purpose is that we're going to talk about the first Heidelberg system. So now we already mentioned that this is the character, the F orbit. This is the F orbit inside M star. The character group of M. This is the all the in other words that you take the you have to define this by the component degree and so then we can take the so first I will define abstractly. So first we can define the variables are the volume. So you can define this PNB. So in other words, I take the orbit here, and then I declare sum is something like a power sum symmetric function corresponding to these of. But when we define the degree to be n times the degree of these the orbit. The degree of orbit means that this is the cardinality of that orbit. I define that the degree of the orbit. So with these are the power sum. I just so then obviously these are then I have this F. The first one will be the symmetric functions. So in other words, I have lambda with a function. Going to the order orbit and n greater than 0. So in other words, there are many copies. So this is the usual symmetric functions, but then we have these have these. We cancel these. So this is like and then one way to understand these is that the elementary symmetric function. So once you have Pm, so then you can define some elementary symmetric function of the phi. This is the elementary symmetric function. And then by the there is a result by Green using Proulx's famous theorem of lifting characters. This turns out to be exactly a characteristic function for GL, I mean GN d phi. So in other words, these are the real fields. In other words, you can think in the categorically that you can think that these fields are really coming from the characters over here, and they are really characters coming from characters. So in other words, these elements are exactly make sense. Then you have these, and also the power sum will make sense. Okay, so then for the power sum, this space turns out to be we can consider the Heisenberg. Heisenberg algebra. So the reason is because I want to construct all the irreducible characters. The quickest way is to view these as a Fock space for this Heisenberg algebra. The Heisenberg algebra is that I consider this Pm, and this is going to be n. So now I'm going to enlarge that enlarge with so here these are the positive n. So here I mean not equal to 0. So here I allow this n going to all to be integer, and this is n minus n and delta phi and the phi prime, and then times this then times the central element c. So the Heisenberg algebra is generated by those elements when n not equal to 0, plus there's a canonical central element, and this is the commutation relation. So then it turns out that this is the canonical space, canonical irreducible space for this Heisenberg algebra. And for n is so for the purpose, I'm actually flipping the not usual way in Fock space. I declare this Pm to be the usual like minus 1. So this Pm will act as a multiplication operator over here, and the P minus M will be acting as a differential operator. So this is canonical commutation relation. We have these. Okay. So then with that, then how do we construct this irreducible? Well, that's very, this is very easy. So construction of irreducible. So you consider that and then you consider so-called by the Bernstein vertex operator. So for each orbit, define this S D D. And then this, and so now you have these operator, and this turns out to be advocate of this of this space. This is so for this operator, and then we get a canonical. So for each partition, then you have it turns out that for lambda, say each partition, we can define this element. If it S lambda 1, S lambda L, this turns out to be orthonormal. And then they are the so-called the corresponding to the Schur function. So in other words, you fix the orbit, consider just one copy over here, and that's exactly isomorphic to the renal symmetric function. Within that renal symmetric function, this product of vertex operator turns out to be exactly the Schur function. So now, if you want to for the general for the color partition, weighted color partition, I certainly we define similarly. Now we don't have this, so then so this element will be product. And then so you get this element as lambda are exactly of the normal base or linear base for this F, the first for this space. And this space is the exactly isomorphic to R. That's all these all basic object. In other words, we construct some candidates for these irreducible characters. Of course, one thing is not yet settled because we know that all these things are through these Green's result and also based on Brow's result. We only know that these are only the virtual characters. We have to settle that they are actually authentic characters. But that has to be delayed because I really have to calculate that they are really the authentic characters, not just virtual characters. So for that, we have to compute the character table. I mean, at least I need to find the degree. So then I need to go to the talk about the second Heisenberg theorem, second Fock space, realizing the very same space using another Heisenberg theorem. Yeah.
Bernstein vertex operators, do they have a nice categorical meaning?
Yeah, this means like in the sense in the paper with Wei Chang and Equal. That's actually one of the examples of first categorization. One of the first one constructing in a sense, the categorical. We realize these by really characters.
But for this vertex operators, do you say that on representation range?
Yeah, in the using the characters of this real product,
Like induction.
very similar. I mean, for this one, of course, this is easy. Of course, that okay. So now we talk about the second. So we have some candidate. We have these all these the Schurs. Now we go to the return back to these. We want to talk about what about the conjugacy class, the characteristic functions. Well, it turns out that we already mentioned that this guy, the Pn, we know that they are some character class and characters, virtual characters for the. I mean, in the general sense, that these are the for the GL and GNEB on these. So then, one way to do that, I can go to first of all view these as doing sort of something like taking the Fourier transform of this guy over the multiplicative group of degree n times dp. So when you introduce some element of PNF, so I do the quote unquote. So essentially, this is the. So now I'm going to take the F, that's the orbit in the F orbit in the field, for the field. So then you take these, take the discrete Fourier transform. So I, of course, the exact formula, there are some cases, but essentially it will be some formula like this. So now, in other words, I just got another element of the still inside the same space. So now you can ask what are the so then you can also ask what are the computation relations for this element. So first we have to embed this into that in the Heisenberg algebra over that. So it turns out that we have the.
You have an X. What's the X?
Oh yeah, X is the. I take the element in the. So here X is the. So this is the orbit. Now you take any element inside the orbit. The element inside the orbit. So. So then, now it turns out that within the same the one, we have proved that this guy take two orbit, and then in other words, I'm going to be lifting this to the Heisenberg, and then turns out that this is the so then you have this computation relation. So no matter because actually everything is this is within the Heisenberg. So within the in other words within the same Heisenberg algebra, but using based on these computation relation. After you do the Fourier transform, then you find out this. So so clearly, I can realize these as the original space R is actually isomorphic to. So first, we have this. So this is the first one. Now we're going to have this second one. Now this is the generated by this.
How do you define the kernel? How do you define that transform? That none of the, how do you define
Yeah, that's a you take a
the trace?
you take that's a pairing. There's a pairing between the multiplicative group and this character. For that pairing, and then you define this. So that's the essentially this is you averaging over the character. That's the Fourier transform. And then of course so this is also a graded space, but graded by this detent. I mean this is graded by this, and then sum over this. Okay. So over here, this is defined exactly the same as the last one. So here you take the and then so here the degree is exactly the degree of the irreducible polynomial. And over here the orbit corresponding to the irreducible polynomial, and this is exactly the degree of the irreducible polynomial times the weight of that partition, colored by the orbit F. So and then so we can introduce the so for each F in the orbit, then introduce the vertex operator for Hall-Littlewood. So this is the so you introduce this. So for simplicity, I'm not going to always write down this Q to the so the QF is a Q to the degree F. So we have this and yeah, C10. Due to the normalization, we have some QF minus M. So then we also get the component E. So you know this is very similar to this Bernstein vertex operator, except that they have this multiplication. So it turns out that you have exactly similar thing happening. So like over here, you produce some basis, the orthonormal basis from the Bernstein operator. For this vertex operator, for the Hall-Littlewood, corresponding to, it turns out that for each and there's a Q lambda for the partition. This is equal to product. So these are also orthogonal, not orthonormal. Under these, under that in the product, under this in the product, and under the in the product with the under the product determined by and so and then you extend this to the order the product. So and the first one, this is the first thing. The second, and then you take all the product. And this will be orthogonal base inside. I mean, in the for this for the second box space. And it turns out that for this one piece, these are exactly corresponding to the Hall-Littlewood symmetric function. So now we define this to be the dual base, dual base to this one. So in other words, now the claim is that of course that the Green's original result to prove that these actually represent the conjugacy class took a lot of work, and also this actually McDonald actually essentially you can view this 3 chapters of McDonald's book by actually proving that these are the right symmetric functions representing the conjugacy class. So now we want to do it in a quicker way. So one thing we can do this at this is a of course using vertex operators. So to do that, we introduce the This introduce a half vertex operator. This E F. So F again is the orbit. It turns out that these are exactly corresponding to the elementary symmetric function. Or Schur functions corresponding to the one column. What's that? Now, what is this whole algebra? I mean, the green step. They're talking about the structure constants is that the multiplication of two characters. So we have to define some multiplication operator, similarly multiplication operator within this space. So then for the but this is a so the you can also define the for the so for any symmetric functions, you can define something like the adjoint operator of the multiplication by f. So if you have a symmetric function, and then you multiply the base and then define this the adjoint of that. Okay. So now it turns out that so to identify to show that these are the right bases, I really have to worry about what are the generator. These are the generator of these for the elementary symmetric function in the multiplication. So I need to find out the adjoint action of this guy on the Hall-Littlewood function. If we can really compute that the structure constant to prove they are exactly the right one, then we have a very quick and short proof of Green's theorem. So that's indeed the case. So so first of all, we have a lemma. So for each R, and then the action of E R of this are exactly given by this formula. So to define this, at first I look at the operator. I define this as this is the product of all the vertex operators corresponding to the rectangle. And then this turns out to be M. So R Q inverse Q M minus R M minus 1 R and E R. So there's a commutation relation between these two. And this, of course, this actually, the proof really comes from when we got these Hall-Littlewood. There are some commutation of Hall-Littlewood. So you just use that commutation relation plus the you compute the action on the these operators. Then you can prove something like this. So once you prove these, then we have the following theorem. So for each, I'll just write a partition for the simple. I did not even write on this orbit. So this is so that it turned out that this action acting on general Hall-Littlewood. I mean, this factor, and then this is exactly mu and I. And while these run through all these mu such that the mu mod mu is a clinical R script. So then using these, then we got the theorem. Of course, this is a ring. But using the current one, this the new proof by using this vertex operator, and these are exactly so this if you define this pi, map this pi this over this p lambda bar is an isomorphism. So in other words, we realize that this space as a established isomorphism between R of this whole. So once you have these, then of course then still one thing is not settled that we have to really prove that our Schur functions that they are really representing the irreducible character. For that, so of course, one thing to do, that typical thing to do is to compute the degree. You compute the conjugacy class. I mean, compute the character, the virtual character. Take the inner product with this with the conjugacy class representing this column, the row. Then you want to prove that's a positive number. If you prove that's a positive number, then this Schur character exactly. They are exactly indeed character. And we also got all the irreducible character. And so to do that, we can do in the most general case, I mean, we can present a way to compute the characters using vertex operator. By the way, I want to make so here when we have irreducible characters and also the class, the Green's work was so. It's remarkable that they actually compute all the characters. I mean, in a sense, determine all the character values. Although, I mean, there's no explicit way to compute the characters at that time. So to show that so of course I know that most people care about the so-called equivalent class. And what are the equivalent class? Equivalent class is this corresponding to the support is just equal to t minus 1. So it's very simple in this picture. But of course, when we do not just an equivalent, we do it for all the class. So now let's talk about the character value. So this first of all, so for the weighted, suppose you have a weighted color partition, and this you have a irreducible character. And then you have this then this on the clouds. And by those by that the previous work, I mean by this, now we already know that these are really and then this P. The inner product is living. So the thing is that how do we compute this inner product? Now we have a general result.
We need to wrap up soon, over time already.
Oh, yeah, I just, okay. So I just say that we have a explicit formula. For these and then the particular case, the degree is it agrees with the Green's formula. So I think that's
Any questions?
Does the vertex operator approach lead to formulas for more structure constants in the Hall algebra?
yeah, that already this are exactly they prove the whole structure constant for Hall algebra.
So this is for one of the partitions being.
Yeah, then you can use that because these are all the products of this operator. You can move on, you see that the move on the EI,
I see.
and then so you got this. Yes.
You think about some applications of Fock vertex operator on the general, I mean, on the general linear group.
Yeah, that actually. This is only for the, this of course, this is just for hybrid.
So in this approach, you avoid Green's polynomial, Green's function altogether, or?
Yeah. Yeah, but this formula build the Green's polynomial.
You recover this?
Recover that the Green has a degree formula. So in the very special cases, Green's degree formula, we have a very explicit formula to write down. Of course, the double sum of all the color partitions and things.
Okay, if no more question, let's thank speaker and other speakers. So it's the end of the conference.
Yeah,
Okay.
yeah, I would like to have a vote of thanks for the local organizing committee. That's usually the Bernstein, Yang, and Jennifer.
So, yeah, we have a free afternoon, and if you are continuing for the next workshop, and there are free bagels also outside. If you want to just grab something and on your way out,
Yeah.
Okay.